Hi everybody, I'm Loïc Potier from the Information Science Institute at the University of Southern California, and today I'm going to talk about modeling the performance of scientific workflow executions on HPC platforms with burst buffers. This work is a joint work between the Information Science Institute and the University of Hawaii. So I will start with an introduction. I will then present our experimental setup and use case. I will then present my real experiment results, talk about our simulator and model, show our simulation results, and then I will conclude. So as you know, scientific workflows are becoming increasingly important for large-scale sciences, for reproducibility and performance. However, because of machine learning and AI, scientific workflows are more and more I/O intensive. Unfortunately, the gap between compute and I/O performance in current HPC system is always increasing. To face this issue, many HPC centers have adopted burst buffers. A burst buffer is an intermediate storage layer between a parallel file system and the main memory. In the current HPC landscape, you have two designs, the shared one and the on-node one, which I will detail later. In this talk, I want to answer the following question: how to estimate the impact of the different burst buffer architectures on workflows performance? The approach chosen in this work is the following: simulation. So our approach works as follows. We first start by doing some execution on a HPC system with burst buffer. From these runs, we extract some workflow execution traces, and we use those traces to calibrate our simulator. Why simulation? The main advantage of simulation is the possibility to explore the heuristic space at scale easily, because it's very hard to do an experimental campaign on a real platform if your workflow is complicated, takes a long time to run, etc. Now I will talk about the experimental setup and use case. So the first burst buffer design is the on-node burst buffer design, which is basically each compute node has a dedicated burst buffer, a private storage accessible only from this node. As you can see on the figure on the right, the burst buffer are in red and the computing unit are in green. So this mode has the advantage to be easy to understand. It's just a dedicated storage, and it has the best performance because you don't share the burst buffer with other users. However, you can have some potential underutilization, and it's more complicated to come up with a good data placement because you cannot easily share files between burst buffers. The second burst buffer design is a shared one. So in this burst buffer design, you don't have dedicated burst buffer on nodes, but all the burst buffers have been gathered into several servers called BB node, and each compute node has to access those burst buffer nodes if they want to use and communicate files on the burst buffer. So this mode is easy to use. It appears as just a file system to the application, so you don't have to do code modification to run. It's full POSIX compliant. However, the performance are not easily predictable due to the bandwidth sharing. And it's a very complicated architecture. It's easy for the user, but it's complicated under the hood. The shared burst buffer design proposes two access modes. So you have the private mode and the stripped mode. So basically in the stripped mode, the files are stripped over multiple burst buffer nodes. So a file is cut into many slices, and each burst buffer holds one slice. And in the private node, you have only one buffer node that holds all the file. So now that I have described the burst buffer setup, I will describe the scientific workflow. As a SWARP example, it's a cosmology workflow using large-scale sky servers. It's a very simple workflow with only two main tasks. So you have two tasks per pipeline, resample and combine, and a SWARP workflow is composed of many parallel pipelines. So the resample task takes as input 32 input images. So you have 16 input images and 16 input weight maps. And the combine task takes 32 images as well and output 2 output files. So now I will present quickly some results from our experiments. So the first result is a comparison when varying the number of files in burst buffer. We only consider the resample task here with 32 cores, and in the y-axis we have the execution time in seconds, and in the x-axis we have the fraction of input files in burst buffers from 0 to 100, and we do it for the 3 burst buffer design: private Cori, striped Cori, and on-node on Summit. The colors of the line distinguish between if we store the intermediate files of resample in the burst buffer or in the parallel file system. So what we can see here, it's like, obviously for private Cori and on-node Summit, it's much better to use the burst buffer, and the more you allocate in the burst buffer, better it is. And however, for the stripped Cori case, it's a little bit different. It's counterintuitive because it's better to not use the fast storage. It's better to use parallel file system. And it's because as we strip file, and in the swap workflow we don't use very big files, it's counterproductive to strip small file. Basically the middleware will spend its time to fetch back pieces of files all the time. The second result is a comparison when we increase the number of pipelines. So the goal of this experiment is to study if we have some contention when we execute many pipelines in parallel. And we do have some contentions, as you can see on the resample and combine case. We can see that when we increase the number of pipelines for the Cori case, so private and stripe, we can see some contention. Finally, a last result to illustrate the difficulty of measuring I/O on a shared machine. So this plot shows the resample variation when we vary the number of pipelines. So it's hard to tell the colors, but the lowest result is Summit, then it's Cori private, and the worst result is stripped Cori, and it's also the result that shows the more variability with a higher standard error. So that shows that the strip mode, because of this strip aspect and because you share the bandwidth, it's harder to have some predictable results. So some takeaway from this, the performance is highly dependent on the access pattern, which is an expected result. When we increase the number of pipeline, we have some bandwidth saturation, even though the usage is far below the peak. So it implies that the classic communication model, latency plus data divided by bandwidth, is likely to not be accurate. Finally, due to its shared aspect, Cori design is easy to leverage, but it's difficult to achieve good performance. On the other hand, Summit design is better from a performance and stability point of view. So now that we have our workflow execution traces, we need to pay attention to our simulator. So for the simulation part, we rely on Wrench. So Wrench is a simulation toolkit that is able to accurately simulate complex distributed systems, and it's easy to use. It has a nice API, and Wrench relies on the well-established SemGrid framework for the whole software and hardware stack. So you can go check out what they are doing. It's a really cool project. It's under active developments. So how do we calibrate the simulator, which is the main task if we want to have some accurate results? So the simulator takes as input the sequential compute time for each task. So you need to give to the simulator a DAG, so a graph that represents the workflow, and each task must be annotated with its sequential compute time. And the simulator will simulate all the I/O overheads, network overheads, and compute overheads. So this time is denoted as TCI1. However, our real experiments have recorded the observed execution time on P-core for each task, denoted as TIP. So our goal here is to go from TIP to TIC1 to be able to instantiate our simulator. So how do we do that? That's what we'll discuss in the next slide, but first I will take a few seconds to discuss something. So we do not aim at providing an analytical communication model in this section. What we want to do is to determine a first-order approximation of the raw sequential computational time. What I mean by raw sequential computation time, it means sequential computation time without any I/O. So TIC1, basically. So how do we decompose TIP and isolate TIC1? So we have the fraction of time spent in I/O called lambda I/O, the number of cores used called P, the fraction of the sequential execution time called alpha I. So first, we need to take into account the multi-core impact. So we do that with the famous Amdahl's law that states that TICP equal the fraction of sequential time times the sequential time, so alpha I times TIC1 plus the parallel time 1 minus alpha I times TIC1 divided by P. But we can also express the same quantity from an I/O perspective. So TICP is also equal to 1 minus lambda I/O TIP. Basically, that's the raw execution time. We have subtracted the I/O fraction. Then, when we equate each right-hand side, we obtain this formula. And we take a final assumption. We consider that our applications are perfectly parallel, so they scale perfectly. This means that alpha I equals 0, and we can simplify our expression, and we obtain this expression. So now that we have our expression, we can start our simulation. So we have used these parameters found in the literatures. We also have found the value for the alpha I/O, so the I/O fraction in the literature. Now I will present our simulation result that will assess the accuracy of our simulator. So the first result I'm gonna talk about is the accuracy when varying the number of files in the burst buffer. So in green you have the simulated maxspan, in blue you have the measured maxspan. In the y-axis you have the fraction of files, of input files in burst buffer, and on the y-axis you have the execution time as always. So we can see that for private and unknown mode, the average error is around 5-6%, and the standard deviation is around like 3 to 4%, which is very good. However, for the stripped case, we have a higher average error, about 13%, and a higher standard deviation, about like 5%. So we can explain this as follows, because as I said before, the stripped mode incurs more variability and less stability. So it's harder for the simulator to take into account that kind of thing, and we need to work on this and to improve our simulator by implementing a more complex stripped mode into our simulator to mimic what the create data wrap runtime is doing under the hood. However, it's still good accuracy, it's below 15%, so it's not that bad. The second result is the accuracy when varying the number of pipelines in parallel. So these results actually are interesting because they will show if our simulator takes into account the potential contention at scale. And we can see that it does, because the trends are very good, they are very close. So average error is a little bit higher because we do not fully take into account the contention, but it's still under 15%, so it's quite good. And the standard deviation is around like 7 to 5% for Cori and under 2% for Summit. So Summit is very stable due to its private aspect. In addition of those accuracy results, we also perform some validation results. So to validate our simulator, we used bioinformatic workflows called the 1000 Genomes workflow, which it identifies mutational overlaps using data from the 1000 Genome Project, with the goal to find disease-related mutations. So here we've compared some old runs we did for another paper using the 1000 Genome workflow on Cori with burst buffer to what our simulator would predict to see if we are close or not. So the first result I will discuss is just a comparison between Cori and Summit. So this results show what our simulator predicts according how much input files are staged in the burst buffer from 0 to 100%. So this instance of the 1000 Genomes workflow has 900 tasks with a total input data size of 52 gigabytes. So we can observe that Cori and Summit follow the same trend. So more you put files in the burst buffer, the faster you go, which makes sense. We also observe that Cori reaches a plateau after 18%, much faster because we are saturating the bandwidth, and Summit reach a plateau close to 100% because Summit burst buffer has a higher bandwidth. So in this plot I will compare the performance predicted by our simulator for Cori and Summit. So this time I don't plot the execution time, but I plot the speed up when we use burst buffer. So in red we have Cori performance, in black we have Summit, and in blue we have the previous data from the previous study we did. So we only did run for a limited workflow size between 15% and 25% of the total data size. So that's why the blue line is very limited. So that's why the blue line does not span from 0 to 100%. However, even though this validation is limited, it shows that we have an average error of 28%, close to 29%, which seems big, but regarding that it's not the same architecture because Cori has changed. We didn't calibrate our simulator for this workflow. It's a very different workflow from the swap workflow, and it's a very limited validation because it only goes from like 15% to 27%. It's not that bad actually. So we intend to pursue this validation by running the 1000 Genome workflow from 0% to 100% and to compare our result with what our simulator is predicting. Now I will conclude. So in this work we have explored the impact of next generation I/O systems on the performance of some high-profile workflow applications. We've performed a comprehensive analysis of a proxy workflow on 2 different burst buffer systems. We've calibrated, validated and evaluated the accuracy of an open source simulator for both burst buffer architecture. And we have also discussed an I/O-intensive model and a methodology to calibrate our simulator. The next step is to use this simulator to explore the heuristic space of data placement strategy and scheduling strategies. Thank you for your attention. You can join the Slack channel of the conference and ask me questions during my session. You can also contact me at lpotier@asi.edu. Thank you.